All right, welcome back. Our next topic is dealing with the expected value, okay, which is another way of saying the mean or the average value of a random variable x. All right, so in previous lessons we've talked about the average or the expected value of items with the same equal likely outcome, the same probability of occurring. What we're looking at now is a more general equation for this. Okay, and so the formulation that you'll see written for this is that E of x is equal to, and usually we write this as some population value because our expected value is what we expect for the population. All right, and then we're going to sum all of the x values, take the quantity of x multiplied by its probability. And like I say, in previous examples, we had the probability of x being constant to every value of x. And so that's how we could come up with the equation that was, sum of the xi over the number of n's. Okay, because what's really happening is that formula looks something like xi times the probability of xi all over n times the probability of xi, right? And those two terms ended up canceling out of those because I could factor that common term out. And so that's where that was coming from. Okay, so this is the more general version of it and the more powerful of the two. All right, sometimes we can refer to this as a centroidal calculation, and you've seen that in your static centroids, the sum of ai, yi, that was an average value. You're kind of looking for a weighted average, which is the other expression that you'll see this listed as. So a weighted average is what this is called. All right, now we can go to a more general version. So this was for our random variable x. I can have for any function that is a function of that x value, the expected value of h of x, then it's the sum for all of x of the function with x substituted in times the probability of the value with that. And I'll show you an example here in a second to kind of explain it, but this guy does a lot for you. Okay, and it's definitely the most used form of the calculations for expected value that we're going to look at. So let's try one and kind of illustrate it. It's really simple once you've seen it done a couple of times, and that's what we're going to do. So what I have is I have an example that is a distribution with random variable y this time and the corresponding probability of y. And so I've written down a couple of values here, 0, 1, 2, and 3 for my y's, and their corresponding probabilities on here. Now, I'm bound by all the probability rules, okay? I must account for all the sample space being equal to 100%, and, must be positive values. All those same axioms still apply on this. But what happens now is this value of 0 can now have a different probability than the 1, which has 0.25, and the 2 that has 0.1, and 3 at 0.05. They don't even have to be the same anymore. Okay, and so if you look at this is, a probability function that's looking kind of like, like that. That's my distribution function, 0, 1, 2, 3. Here's my y. Here's my probability of y. And that's kind of what this function is starting to look like. Okay, and so again, we've left the realm of everything having to be equal. If you remember our dice example, where we had 1, 2, 3, 4, 5, 6, the probabilities of all of these were all the same value. Every single side of the dice for a fair dice had the exact same value, and that's why we were able to do this equal likely outcomes on this. But we want to be able to handle this case, and that's why this is important. All right, so back on track here. To find the expected value of y, then, all I'm doing is I'm taking, the formula says, if you look, you take the variable multiplied by its corresponding probability, and you do that for every value of the variable. All right, so all I'm doing is I'm doing 0 times 0.6, that's the first term, 1 times 0.25, that's the second, 2 times 0.1, third, 3 times 0.05, which is the fourth term, and then I add it all together and mathematically at 0.6. That's all we did, and you can see I kind of wrote out the expression down below of what we were looking at. So just the y1 value, its corresponding probability. That's it. That's all the expected value is if you know the probabilities. Okay, for a function, let's suppose now that we have a function that we're going to call s sub y. Okay, maybe it's the sum, or it's some calculation that I need to have done that's equal to 100 times y squared. Let's find the expected value of this function. All right, so the expected value of my function s sub y is 100 times 0 squared. So that's the substitution of y1 into that equation multiplied by the probability of y1. So this part never changes. It's just that frontal piece that does. Okay, so we can continue this for the rest of the way. So 100 times 1 squared times 0.25, 100 times 2 squared, 0.1, 100 times 3 squared times 0.05 is equal to 110. All right, and so that would be my value. Now again, you have to track the units. The units of this calculation will carry the same units as the function. So if this had been, you know, a feet cubed kind of thing, then I would end up with a feet cubed down on the other one. Right? But that's the expected value of S of Y. It's really, really easy, and it's the same basics. Okay, and these become important because this is one of the defining characteristics of some of these probability distribution functions. And in fact, if I can classify my data into a particular form, then there are shortcuts I can use to get me the expected value, to get me the variance, to get me those kind of calculations. All right, so that's what an expected value is trying to do for us. All right. Okay, some of the properties that we have for expected value look like the following. I'm going to define a constant a and b, and then my random variable will be x in this. That if I have an expected value of a constant a multiplied by x, I can pull the a outside, and that becomes a times the expected value of x. And likewise, I can do expected value of a constant plus x, x plus b, and that's going to be then the expected value of x plus the expected value of b. But this guy, the expected value of a constant, is just the constant value itself. That's why it's constant. So expected value of x plus b. And then I can put all three together, that e times ax plus b is then a e to the ex plus eb, which is now aex plus b. Okay, and that's it. So these will be some really handy little tools that we'll take advantage of in some of the problems coming up. Now, one thing to point out is that the expected value of a function is not the same as plugging in my expected value into the function. All right, you can't make this mistake. That's, you know, this one happens quite a bit. Okay, so don't fall into that trap. So that's kind of our note to remember about these ideas. You've got to get things into a form that looks something like that. Okay, and you have to kind of split it up this way. All right. Okay, so that's our measure of the weighted average. Okay, we can also do the variance in a similar fashion. So let's just kind of walk you through where this is coming from. The variance of x is equal to sigma squared, and then this becomes kind of, if you remember, we had that, you know, data point minus mu quantity squared thing happening back in our original set. Now we're taking that and multiplying it by the probability of my random variable. All right, and again, the variance, if you remember, is a measure of how spread out the data is, and so we're looking to sum up all of those distances for every single point on the curve. Okay, and so if I go through this, I saved you some algebra, but the algebra, this becomes then the expected value of the random variable x minus mu quantity squared. Okay, and so what we can do is we can go in and look at the standard deviation. Then we know it's the square root of that guy, so sigma is the square root of sigma squared. So this is the square root of Vx. Okay, and so, like I say, as you recall, the variance was always kind of an issue to calculate. It's a little bit cumbersome, if you will, not hard, but took a lot of work. There is a shortcut method that works, okay, assuming that our population mean is a constant value. I can rewrite this if we start off with that first derivation that we had, and I can expand all of this into x squared minus 2 mu x plus mu squared. What happens is that I can expand this, and then I can use those identities and say, okay, well, all I do is take the expected value of this plus the expected value of this plus the expected value of this. I can pull all the terms out separately. Okay, and so what happens is we get the expected value of the variable x squared minus 2 mu. Now, again, we're saying that this is constant. Okay, and then the expected value of x, we said that was the same as my mu of x, so that is mu. Okay, and then plus mu squared. And so if I do the algebra, I get the expected value of x squared minus 2 mu squared plus mu squared. And then I get the expected value of the quantity x squared minus mu squared. And if you remember that this guy was just simply the expected value of x, okay, multiplied by that guy squared. And so a shortcut version is the expected value of x squared minus the expected value of x quantity squared. Okay, be very careful. Notice where the brackets are. This is pretty cool because you're almost always calculating that guy anyway. So all you have to do is do it one more time for x squared, and you're off to the races. So if you do a spreadsheet, just run it for the data that you have and then run it for the square of the data, and you can very quickly get the spread of the data or the variance on this. All right, the properties are a little bit easier. We're going to jump just straight to ax plus b, okay, and the variance of this. And so what happens is this becomes, when the a comes outside of this, it gets squared, and then that's multiplied by the standard deviation squared. And then notice that the b vanishes. There's no b because the b represents basically a horizontal shift of my curve. So if that's my equation and all of a sudden I go and do this and I shift it by b, but it's the same curve, again, these are relative. That's what we're trying to measure. Those distances are still relative. They're the same. Okay, so it's the same curve displaced. The variance will be the same for the variable, regardless of where this curve is in relation to each other. So that's all the b is doing. So the b means nothing. So just put an a squared on top of this, and we're in good shape. Okay, all right, so that's our situation there. All right, so let's try one and kind of see what we can do for this. Okay, so we've got some data. Okay, and this came out of an example that was involving hurricane evacuations from a major city area. So maybe this was, one of those hurricanes that hit, southern Florida, or the one that went through Houston a few years ago. But, basically, we're going to define y as the evacuation time measured in hours. Okay, and so I'm not exactly sure how they would pick up this data. It's probably an after-the-fact measurement, survey or poll or something that was done that, people said it took them 13 hours, 4% of the population, 14 hours, 0.25, 15, 40%, 16, 18%, and so forth, 17 and 18, 10 and 3. All right, so what we'll do is we want to be able to find the mean, the standard deviation, and then the range of expected values, okay, assuming that the range is defined as 95% of all of the data points. Okay, and I'll show you an empirical rule and where that's kind of coming from. All right, so very easily, again, all we're doing for this, if I can get this curve down where you can see stuff, is that the expected value of y, again, is just the y variable times the probability plus the y variable times the probability. And you do that for all values of y. Okay, and when I do that, that's 13 times 0.04 and 14 times 20.25 and 15.4, and you can read the rest of this. And if I do the math on this, it becomes 15.14 hours. So the expected value of y is 15.14 hours. That's kind of where the expected number is, kind of the weighted average of this particular distribution. Now, it's kind of interesting if you look at this, the data, and assume that everything were uniformly distributed, you would expect the middle to occur at somewhere around 15.5 if it had been uniform, right? The midpoint of this range falls there. Okay, well, what the 15.14 is saying is saying that we're less than that value. So this has a slight skew to the left, that there's more probability less than 15.5 than there would be greater than 15.5, according to the way this data is shook out. Okay, all right. So again, it's little things that you can determine. Okay, now we can go in and we can do the variance. So my variance of y is equal to sigma squared, and if we go back to our formula, E times y minus the population mean quantity squared. And so here's our formula. It's that quantity multiplied by its probability. And so go through we're going to take advantage of our shortcut formula just because it's easier to use. All right, so I already have this term. That one's done for us. Okay, so now all I do is calculate the expected value of y squared. And you'll see that it looks a whole lot like expected value of y, except now I'm doing 13 squared times the probability and 14 squared times the probability, and so forth and so on. And if you think about it, all we've done is we've come in and said that my h of y function is equal to y squared on that. Okay, and in the first case, up here, it was actually, we were doing an h of y, we just said that it was y. Okay, that is a valid function. So that general formula for the functional form of this is very, very easy to use and very, very common. It will work for anything. Okay, and so when I calculate the expected value of y squared, that's 230.46. And again, the units on that are hours squared. And then I can calculate the variance or the standard deviation squared as being the first term, e of y squared, minus the value that we got up here, the 15.14, that quantity squared, and I'm left with a variance of 1.24 hours squared. So the standard deviation is just the square root of that number. It's 1.11 would be my standard deviation. It gives you a sense of the spread of the data. Okay, now there's some things that we can do with playing with this. Okay, with some meaning and what's the significance of the standard deviation. It's nice to say, yeah, my data is spread out a certain amount, but what does it physically mean? And we'll show you statistically what that is here in a second. All right, so the third question then has to do with the range of expected values. Okay, and that leads us to the empirical rule. Okay, and so we're going to assume that the data is approximately normally distributed, meaning it has more probability in the middle than it does out on the end. It's not heavily skewed. Okay, and this is what we call a normal distribution or a mound distribution. You may have heard it called as the Gaussian or something. It doesn't have to be exactly that, but it should be reasonably close. And the closer you are, the closer we are to this empirical rule. In fact, later on, we're going to talk about something called the central limit theorem, which says, when I get into sampling and statistics, that if I take enough samples, all data will tend to that arrangement based on the sample that I'm choosing. It's kind of a cool little law that we're going to take advantage of. Okay, but for now, there are three little facts that go with the empirical rule. The first one says that approximately 68% of all measurements will fall within plus or minus one standard deviation of EX. All right, so EX is the expected value. So if I draw that in here somewhere, then if I draw a line here and draw a line here such that that distance is sigma, or a width of 2 sigma centered at E, that 68% of all of the data in the population will fall within that range. Well, that's kind of cool. So that gives us so that's x plus or minus sigma. Okay, the second rule says that approximately 95% of all measurements will fall within 2 standard deviations. So if I go out to here and I go out to here, now I go another sigma on there. Now I've gone 2 sigma, and over here I've gone 2 sigma, that 95% of all measurements will fall within that band. All right, so that's x plus or minus 2 sigma. Okay, the last one is the one that gets kind of interesting. It says almost all, it's more than 99%, probably like 99.9% of all measurements from a population will fall within plus or minus 3 standard deviations of the EX for the population. Okay, so now we're talking x plus or minus 3 sigma. So if I look at that, what they're saying is that if it's the same picture we had up above, here's my expected value, and if I go 3 sigma below and 3 sigma above, the area bounded by these guys in that region right there, it's 3 sigma below, 3 sigma above, or a total of 6 sigma. 99.9% of all the data will fall within that band. And that's kind of cool, because now I have a test for determining an outlier. Suppose you have the numbers 1, 2, 3, 4, 5, and 100 on there. These guys will fall within that realm, but this one is going to be, located out here somewhere on there. And that now becomes a test to say, okay, there's something wrong with that data, because statistically speaking, I know that 99+% of all of the points should fall within that band. Unless I just got unlucky and chose the one that was way out of the end, but you'll know what that value is. So that's kind of a cool little test that we can do. All right, so for our data example with the evacuation time, we can go and look at the range of values, and we said that we wanted 95% as a good estimate of my range of values. So we're going to take the expected value of x plus or minus 2 sigma. All right, and so on this, if I do that, that becomes 15.14. That was that expected the expected value, or the weighted average of that table, plus or minus 2 times my 1.11 hours. And so the range then becomes 12.92 to 17.36. So 95% of all of my data I would expect to fall within this range on here. And that's pretty cool. All right, now just for comparison, let's take a look at what happens if I go to 3 sigma, which would be all of the data points. So a range of 15.14 plus or minus 3 times 1.1 hours. That gets me in a range of 11.84 to 18.47. So I would expect all of my data to fall within this point. So if somebody reported that it took them 9 hours, to get home, you'd be looking at going, yeah, unless you can prove to me why it was so much shorter than everybody else, I would call BS on that. Okay, now again, statistically speaking, it's possible that they were 9 hours, but if you start getting multiples, then you need to go back and look at how your data is being calculated. Or if somebody said it took me 36 hours, you go, no, something else was going on. You stopped for lunch, or took a picnic, or whatever the case may be. Those would be kind of the things that you're looking at. But these 2 sigma, 3 sigmas are very, very powerful. Now, in fact, in manufacturing, this idea that all of my data falls within a 3 sigma window has led to the idea behind 6 sigma in manufacturing. It's a process by which, they set up for, just-in-time delivery, and they're designing for these bands, and then outside of that, they're using that as a prediction model in the manufacturing environment. So you may have heard of 6 sigma or a 6 sigma black belt or something, and there's a lot more to it than this, but that's the general basics of what this idea is of 3 sigma. All right, so that's kind of cool. All right. Okay, so now you've got a test for the outliers, and you've been able to figure out kind of the range of expected values for those. All right, so that's all we've got for this lesson. That's our expected value calculations. So a little bit shorter, but hopefully reasonably clear. Very, very powerful concept, and you use it all of the time in probability and statistics. So we'll be coming back to this video, or at least the content of this video, over and over and over again. So with that, we'll leave it there for today. Thanks for your attention. As always, if you like the video for me, that would help us out. Leave us some comments down below, and then as always, subscribe to the channel if you haven't already. We would greatly appreciate it. Hope this helps. Have a great afternoon. Happy engineering.